That beautiful nebula is a cosmic lie. Its gentle glow masks a violent reality, a celestial engine of chaos and contradiction. This is the Crab Nebula, the expanding wreckage of a star whose cataclysmic death was seen from Earth in the year 1054. It floats 6,500 light-years away, a permanent scar in the constellation Taurus. For decades we thought we understood it, but we were wrong. Today we are going to journey through 50 of its most bizarre and unexplained phenomena. You will discover ghostly glows that defy physics, cosmic accelerators that should not exist, and a central pulsar spinning with impossible fury. What strange force creates flares so powerful they double the nebula's brightness in mere hours? And why does the very heart of this system seem to move faster than light itself? By the end, you will see a familiar cosmic landmark not as a quiet remnant, but as the universe's most dynamic and confounding puzzle. What does it feel like to watch a mystery that refuses to be solved? At the very center of this chaotic cloud lies the engine of it all, a cosmic dynamo of impossible power. This is the Crab Pulsar. Picture a sphere of pure neutron matter, a collapsed star core so dense that a single teaspoonful would weigh as much as a mountain. Now imagine that entire mountain compressed into a city-sized sphere, whirling around at a staggering 30 times every single second. It is a celestial lighthouse, sweeping twin beams of radiation and particles across the galaxy with every rotation, powering the entire nebula's eerie glow. But this incredible spin rate is the first great puzzle. How can an object with such immense density, with gravity strong enough to crush atoms into a soup of neutrons, spin so furiously without tearing itself to pieces? The forces involved are almost beyond comprehension. It is like spinning a bowling ball so fast it completes a full rotation in a mere fraction of a second. Except this bowling ball is made of material harder than diamond and is held together by the strongest gravity in the universe outside a black hole. The very fact it exists in this state challenges our understanding of the limits of matter itself, but the strangeness does not stop with its steady spin. This pulsar has a habit of stuttering. Astronomers call these events glitches. Without any warning, the pulsar's incredibly precise rotation will suddenly, unpredictably, speed up by a tiny but measurable amount. It is as if a perfectly tuned clock, after years of ticking with metronomic accuracy, suddenly gained a few extra ticks in a single second before settling back into a new, slightly faster rhythm. These glitches are profound mysteries. What internal cataclysm inside this ultra-dense star could cause such a sudden change? The leading theories sound like science fiction. One idea suggests starquakes where the pulsar's incredibly rigid crust, under unimaginable strain, cracks and shifts, causing the entire object to contract slightly and spin faster, much like a spinning ice skater pulling in their arms. Another, even more exotic theory involves a superfluid sea in its core. A superfluid is a bizarre state of matter with zero friction, and it is thought that the interior of a neutron star may be filled with this strange substance. The theory goes that this superfluid core can sometimes become unstuck from the solid crust, transferring a massive amount of rotational energy in a sudden burst that we observe as a glitch. Yet despite decades of observation, no single theory perfectly explains every glitch we see. Each unpredictable jump in spin is a reminder that beneath the serene, ticking beacon we observe, the heart of the Crab Nebula is a place of violent, hidden turmoil. Yet even the pulsar's erratic heartbeat cannot explain the nebula's most violent outbursts. In 2011, astronomers witnessed something that should have been impossible. The Crab Nebula, a cosmic landmark known for its steady, predictable glow across all wavelengths of light, suddenly and violently erupted. In just a matter of hours, its output of the highest energy gamma rays, the most powerful form of light in the universe, flared to more than 30 times its normal level. For a brief period, the entire nebula became twice as bright. This was not a gentle fluctuation. It was an explosion of pure energy emanating from deep within the cloud itself, and it completely upended our understanding of how these celestial engines work. The true shock came when scientists pinpointed the source. These monstrous gamma-ray flares were not coming from the central pulsar, the obvious powerhouse. Instead, they were erupting from a region far out in the nebula's tangled web of filaments and magnetic fields, a place where our models said such extreme particle acceleration simply could not happen. Think of it like this: you have a single, incredibly powerful lighthouse. Suddenly, a patch of ocean a mile away from the lighthouse itself begins glowing brighter than the lighthouse beam, powered by some unknown internal fire. That is the scale of the mystery. The problem is one of super-acceleration. The pulsar's fierce winds are indeed powerful, but they can only push particles to a certain maximum energy, a limit defined by fundamental physics. The particles producing these gamma-ray flares, however, were reaching energies 1,000 times higher than that theoretical limit. It is as if a child's slingshot, designed to launch a pebble across a yard, somehow fired that same pebble into orbit. Something within the nebula is acting as a hidden, ultra-efficient particle accelerator, far surpassing the power of its own central engine. So what could this hidden cosmic slingshot be? The leading suspect is a process called magnetic reconnection. Picture the nebula's magnetic field lines as an unimaginably vast, tangled bundle of rubber bands stretched to their limit. If two bands pointed in opposite directions suddenly snap and reconnect into a new, simpler configuration, all that pent-up magnetic energy is released in a catastrophic instant. This violent event could, in theory, whip particles to those impossible speeds in a very localized region, creating a brilliant, fleeting flare. But the scale and power of the crab's flares push even this dramatic explanation to its breaking point. Other theorists suggest there may be an entirely separate, undiscovered structure within the nebula, a hidden accelerator like a natural version of our largest particle colliders, operating in the silence of deep space. Each gigantic flare is a direct challenge, a message from the nebula that its deepest secrets and its most potent energies are still hiding in plain sight. Those impossible flares are just one layer of the nebula's deception. Look closer to the pulsar itself, and you will witness an even more blatant defiance of cosmic law. Surrounding the spinning neutron-star is a region of churning, high-energy plasma, and within that chaos dance strange, sharp-edged features astronomers call the wisps. They are not static. Through the keen eye of the Hubble Space Telescope, we have watched them in time-lapse, and what we see is utterly confounding. These wisps, these ripples in the fabric of the nebula, appear to race outward from the pulsar at speeds exceeding that of light itself. They seem to break the universe's ultimate speed limit, a law we thought was unbreakable. This is the illusion of superluminal motion, a cosmic magic trick played by relativity itself. The truth is both simpler and more profound. The material in these wisps is indeed moving at a staggering fraction of light speed, blasted outward by the pulsar's fierce wind. But it is not moving directly toward us. Instead, it travels at a very slight angle across our line of sight. Imagine a lighthouse beam sweeping across a distant fog bank. The point where the beam hits the fog appears to race across the cloud far faster than the beam itself is actually rotating, especially if the beam is aimed nearly but not quite directly at you. The wisp we see is like that bright point in the fog. The material is moving almost as fast as light, and because each new burst of energy catches up to the radiation from earlier bursts from our perspective, it creates the visual illusion of a feature moving faster than the light it emits. It is a breathtaking geometric sleight of hand, a reminder that in the extreme environment around a pulsar, even our perception of speed and motion can be fooled. Yet understanding the illusion does not solve the deeper mystery of the wisps themselves. What exactly are they? These are not vague clouds. They are sharp, defined, wave-like structures that form and race outward in the shocked plasma. One leading idea is that they are compression waves like sonic booms in the stellar wind. As the pulsar's outflow slams into the slower-moving nebula, it could create standing waves of dense, bright material that we see as these rippling fronts. Another theory suggests they are caused by a magnetic instability, where the incredibly strong magnetic fields around the pulsar kink and snap, lighting up vast sheets of plasma in their wake. Or perhaps they are something else entirely, a visible manifestation of processes we have not yet conceived. Each time-lapse movie from Hubble does not just show a pretty light show. It captures a fundamental debate about how energy and matter behave under the most extreme conditions imaginable, a debate that unfolds in real time just 6,500 light-years away. If even what we see moving is a cosmic illusion, what other truths about the Crab Nebula are hiding in plain sight, waiting for us to view them from the right angle? This strange dance of light and illusion is not the only way the Crab Nebula conceals its true nature. Shift your gaze to a different part of the spectrum, to the realm of heat and long, invisible waves, and another profound mystery emerges. Observations from infrared telescopes like the Spitzer Space Telescope reveal a haunting and persistent glow that simply should not be there. According to our best models, the vast majority of the crab's light should come from a single, powerful process called synchrotron radiation. This is the light created when ultra-fast electrons, spiraling at nearly the speed of light around the nebula's powerful magnetic field lines, release energy. It is a brilliant, efficient engine that explains the nebula's visible and X-ray glow beautifully. But the infrared data tells a different story. There is an excess, a surplus of infrared emission that the synchrotron model cannot account for. It is as if you calculated the exact output of a roaring fireplace, only to discover an unexplained, gentle warmth radiating from the cold stone of the hearth itself. So what is producing this mysterious extra heat? The hunt for an answer has led scientists down several fascinating and conflicting paths. One compelling hypothesis points to dust, but not just any dust. We are talking about the coldest dust in the universe, grains of carbon and silicate that have managed to form and survive in the hostile, radiation-blasted environment of the nebula. These tiny particles would be warmed ever so slightly by the nebula's ambient light, and then re-radiate that energy as a faint infrared whisper. Finding this dust would be a revelation, as it would mean complex molecules are assembling in a place we thought was far too violent for such delicate structures. Another possibility is molecular hydrogen. When hydrogen molecules are excited by ultraviolet light or collisions, they can emit a very specific signature in the infrared. Detecting this would be like finding a hidden reservoir of the original star's building blocks, frozen in time within the expanding wreckage. A third idea is more exotic. Perhaps there exists an unusual, hidden population of low-energy electrons within the nebula. Our telescopes are fantastic at spotting the most energetic, fastest particles, but what if there is a vast, slower crowd we have missed? These lower-energy electrons would produce radiation that peaks in the infrared, potentially creating the observed glow. Identifying the true source of this anomalous infrared light is far more than an academic exercise. It is crucial for balancing the nebula's cosmic ledger, its total energy budget. We need to account for every joule of energy the pulsar puts out, tracing its path from the central engine through the nebula and out into space. This unexplained infrared glow represents a missing entry in that ledger, a significant portion of energy whose origin and fate we do not understand. It forces us to ask what components of the Crab Nebula we are still blind to. Are we overlooking an entire ecosystem of cold matter thriving in the shadows of the brilliant light show? Until we solve this thermal mystery, our picture of this cosmic wreckage remains fundamentally incomplete, its true composition still hidden in the dark. The mystery of the missing heat is a clue that we might be looking at the Crab Nebula all wrong. Perhaps our entire starting point is flawed. We call it a supernova remnant, the debris from a star that died in a single spectacular explosion. But what if the star did not die completely? This leads us to one of the most haunting ideas in astrophysics, the ghost in the machine. Some sophisticated computer models of that ancient explosion suggest a startling possibility. The titanic blast of 1054 may not have utterly annihilated the original star. A remnant of its core, a dense cinder, could have survived the cataclysm and might still be lurking within the nebula today, hidden from our view. Or perhaps the progenitor star was not alone. Many massive stars have binary companions. Could a partner star have endured the blast, now orbiting invisibly within the glowing wreckage of its former twin? Astronomers have searched meticulously for this ghost. They have scanned the heart of the nebula for any faint, cool star that does not belong, for any unexplained gravitational wobble in the pulsar's motion that would betray a hidden companion. So far, every search has turned up nothing. The null result is in itself profoundly strange. If a remnant core survived, where is it? The leading candidate would be a black hole, an object so dense that not even light can escape its grasp, which would explain why we cannot see it. But the pulsar we do see, that rapidly spinning neutron star, is also a perfectly viable remnant of such an explosion. Having both a pulsar and a black hole from the same supernova stretches our models to the breaking point. Another exotic possibility is a quark star. This is a theoretical object even stranger than a neutron star, where the pressure is so immense that the neutrons themselves break apart into their constituent quarks, creating a soup of fundamental particles. A quark star would be slightly smaller and denser than a neutron star and might emit a very different signature, yet our telescopes have found no evidence for one here. The absence of a second remnant forces us to re-examine the supernova mechanism itself. It tells us that the explosion was perhaps perfectly efficient, transforming the entire core of the star into the pulsar we observe and blasting the rest outward without leaving anything else behind. Or it tells us that our methods for finding such a ghost are still inadequate. This unanswered question lingers over every other mystery. Is the pulsar the sole ruler of this domain, or is it sharing its chaotic throne with an invisible king, a dark companion whose silent presence influences everything we see? Until we find this ghost or conclusively prove it was never there, a fundamental piece of the crab story remains a shadow. Even the nebula's outer edges are alive with restless energy. Far beyond the brilliant filaments and the churning central region, the Chandra X-ray Observatory has captured something subtle yet astonishing. Encircling the entire Crab Nebula like a faint cosmic aura is a vast X-ray halo. This is not a static shell of ancient debris. Time-lapse images from Chandra reveal a halo that breathes, a structure that subtly changes its shape and brightness over months and years. It pulses and shifts at the very edges of visibility, proving that the nebula's influence extends far deeper into space than we ever realized. This changing halo forces us to ask a critical question. What invisible forces are at work in this seemingly empty frontier? One compelling explanation involves a relentless leak. The pulsar's furious wind, that torrent of high-energy particles, may not be perfectly contained by the nebula's inner shock waves. Some of these particles could be escaping, bleeding out into the surrounding space. Once free, they would travel outward until they eventually collide with the thin gas of the interstellar medium, the sparse material that fills the space between stars. These collisions would be like high-speed particles striking a nearly invisible wall, generating a faint but detectable glow of X-rays that we see as the halo. The variability we observe could then be due to changes in the pulsar's wind itself. A slight increase in its power or a shift in its magnetic structure would send a different wave of particles into the halo, causing it to brighten or morph in shape. Another possibility is even more dynamic. The halo might not just be a passive screen where particles strike. It could be an active battlefield where the nebula itself is expanding into and interacting with lumps and filaments of interstellar material we cannot directly see. Imagine the nebula as a ship plowing through a faint cosmic fog. As it moves, its bow shock compresses and heats that fog, creating a glowing halo whose shape changes with the density of the material it encounters. The changes Chandra sees could be the nebula encountering denser clouds or ripples in the interstellar medium, lighting up new regions of its halo in real time. This variability adds a crucial and often overlooked layer of complexity to the Crab story. It tells us the nebula is not an isolated island in space. It is an active participant in its galactic environment, both influencing and being influenced by the space around it. The faint, shimmering halo is a testament to its ongoing dialogue with the cosmos, a reminder that even a 1,000-year-old supernova remnant is still writing its history, one X-ray photon at a time. The faint, shimmering halo is a whisper from the nebula's edge, but to understand its furious heart, we must look at light in a whole new way. This brings us to a phenomenon that reveals the hidden skeleton of the entire structure, its polarization. Ordinary light vibrates in all directions, a chaotic jumble, but the light streaming from the Crab Nebula is not ordinary. When scientists measure it with special instruments, they find it is highly polarized, meaning its waves are vibrating predominantly in one specific plane. This is a crucial clue because polarized light is the signature of a powerful, organized magnetic field. As those ultra-fast electrons spiral along magnetic field lines, they emit light that is polarized in the direction of the field. By mapping this polarization across the entire nebula, astronomers have, in effect, drawn a blueprint of its invisible magnetic architecture, and what they found was both elegant and baffling. The overall structure is remarkably toroidal, shaped like a vast cosmic donut encircling the pulsar's equator. It is a field of stunning order and symmetry, woven into the fabric of a cloud born from utter chaos. Think of a hurricane. The winds are devastatingly powerful and turbulent, yet at its core, the storm organizes itself around a calm, structured eye. The Crab Nebula's magnetic field displays a similar, but far more precise, level of organization emerging from the violence. This is profoundly surprising. A supernova explosion is one of the most chaotic events in the universe, a runaway thermonuclear blast that should scramble magnetic fields into a messy, tangled knot. The fact that a clean, toroidal shape emerged and has persisted for 1,000 years suggests a powerful, ongoing force is constantly combing the chaos into order. That force is the pulsar's wind. The spinning neutron-star acts like a colossal magnetic anchor, dragging its ordered field lines out into the nebula as it blows a relentless, high-speed wind of particles. This wind inflates a bubble within the expanding debris, and the magnetic field gets stretched and wound into that distinctive donut shape around the equator. But the map is not perfectly smooth. Within that grand toroidal structure are strange kinks, twists, and regional variations. The polarization vectors, those little arrows showing the direction of the field, do not all point neatly around the ring. In some areas, they are sharply bent or even reversed. These are the scars of battle, the signs that the pulsar's orderly wind is constantly fighting against the inherent turbulence of the remnant and perhaps against itself. One leading theory for these kinks involves instabilities in the wind itself. As the ultra-relativistic flow slams into the slower outer shell of the nebula, it can create shock waves that ripple back inward, distorting the magnetic field like a stone disturbing the surface of a pond. Another possibility is that the pulsar's spin axis and its magnetic axis are not perfectly aligned, a configuration known as an oblique rotator. This misalignment would cause the pulsar's lighthouse beam to sweep through the nebula, injecting energy unevenly and potentially twisting the magnetic field in complex ways over time. Solving the polarization puzzle is key to unlocking the nebula's ultimate fate. A strong, ordered magnetic field acts as a cage, helping to confine the high-energy particles and shape the nebula's beautiful filaments. Understanding its precise structure tells us how efficiently the pulsar's energy is being converted into light and how long this brilliant celestial engine can continue to shine. Each kink in that magnetic donut is a question, a frozen moment in a thousand-year war between order and chaos, with the pulsar's relentless wind fighting to impose its will upon the wreckage of its own birth. That magnetic cage does more than just shape light. It actively reshapes the very physics of the explosion that created it. According to our standard playbook for a supernova remnant, the Crab Nebula is missing a crucial character. When a star explodes, it sends a blast wave racing outward at millions of miles per hour. This forward shock plows into the surrounding space, heating it and creating the nebula's outer shell. But simultaneously, a counter wave should form, a reverse shock that travels back inward toward the center of the wreckage. Think of it like a splash in a pond. The initial outward ripple is the forward shock, the water rushing back in toward the point of impact, creating a secondary, inward-moving turbulence is the reverse shock. This reverse shock is vital. It is supposed to slam into the slower-moving debris ejected from the star's interior, reheating it to millions of degrees and making it glow brightly in X-rays. In most supernova remnants, we see this reverse shock clearly. In the Crab, it is conspicuously absent, or at least it is behaving in a profoundly strange way. The X-ray emission we do see from the inner regions is fainter and more structured than the simple, spherical shell our models predict. It is as if the cosmic pond had a splash, but the water never rushed back in. So where did the reverse shock go? The prime suspect is once again the relentless pulsar wind. From the moment the neutron-star formed, it began blasting out its hurricane of particles and magnetic fields. This wind essentially inflated a high-pressure bubble inside the expanding shell of debris. By the time the theoretical reverse shock tried to form and travel inward, it would have encountered this bubble wall, a barrier of furious, magnetized wind pushing outward with immense force. The reverse shock may have been weakened, distorted, or even completely halted by this opposing pressure. It is like trying to start a wave in a bathtub while someone is vigorously stirring the water in the opposite direction. The pulsar's energy output is so dominant that it may have overwritten a fundamental phase of the remnant's evolution. The implications of this missing shock are serious. Without that standard reheating process, our estimates for the temperature, mass, and total energy content of the inner debris could be wildly off. It even complicates how we date the nebula. The progression of these shock waves acts like a cosmic clock, and if one hand of the clock is broken or invisible, telling precise time becomes guesswork. Some theorists suggest the reverse shock is not missing but hidden. Perhaps it exists in a highly distorted, non-spherical shape, warped into a complex maze by the pulsar's magnetic field, making it difficult for our telescopes to recognize. Or maybe it occurred very early and very quickly before our observations began, leaving behind a faint, cooled signature we have not yet identified. This quiet absence forces a humbling realization. The Crab Nebula is not a standard supernova remnant. It is a hybrid, a pulsar-wind nebula that formed inside a supernova shell so rapidly that it fundamentally altered the shell's own development. The star's death cry was almost immediately drowned out by the louder, persistent roar of the engine it left behind. Even the smallest details within this nebula refuse to stay still. Scattered throughout the glowing filaments are dense, compact clumps of gas known simply as knots. They look like tiny, bright beads sewn into the vast tapestry, but they are anything but static. One in particular, the so-called Southwest Knot, has become a cosmic celebrity for its bizarre behavior. Observed over weeks and months by the Hubble Space Telescope, this knot and others like it do something extraordinary. They flicker, pulse, and change their very shape on timescales of mere days. Their brightness can double or halve in a matter of weeks, and their outlines warp and shift as if alive. This is not the slow, majestic expansion of the nebula as a whole. This is rapid-fire variability happening in pockets of gas no larger than our entire solar system, a frenetic dance at the smallest scales. What force could possibly be puppeteering these tiny structures with such speed? The prime suspect is, of course, the central pulsar. Its lighthouse beams of radiation sweep across the nebula 30 times a second. But the pulsar's output is not perfectly constant. Tiny fluctuations in its powerful wind or in the magnetic field that guides it could change the intensity of radiation bathing a specific knot. Imagine standing in a dark room where a powerful strobe light is spinning. If the strobe light itself gets slightly brighter or dimmer, the objects it illuminates will appear to flicker in sync. The knots could be acting like cosmic reflectors, their brightness directly tied to the pulsar's mood swings. However, there is a compelling alternative. These knots might not just be passive reflectors. They could be intrinsically unstable structures born from the violent turbulence of the pulsar wind slamming into itself and the nebula. Picture a raging river hitting a series of rocks. Behind each rock, the water churns into a persistent, frothing whirlpool. But the exact shape and intensity of that whirlpool changes from second to second as new eddies form and collapse. The knots could be similar whirlpools in the magnetized plasma, dense concentrations where magnetic fields pinch the gas tightly. Their flickering could then be caused by internal instabilities, moments when the magnetic pressure confining them briefly fails, allowing the knot to expand and dim, or when a new wave of particles slams into it, causing it to compress and brighten. This makes them a priceless natural laboratory. We cannot recreate such extreme plasma conditions on Earth, but here, 6,500 light-years away, nature is running the experiment for us. By watching these knots brighten, fade, and morph in real time, physicists can test their most complex models of how magnetized fluids behave at relativistic speeds. Each flicker is a data point, a clue to understanding how energy dissipates in this chaotic environment. The fact that we see this happening at all is a testament to the nebula's relentless dynamism. It proves that the Crab is not just a large, slow-changing cloud. It is a hive of microscopic activity where even the tiniest features are caught in a storm of change, telling a story of illumination and instability that unfolds not over centuries but over days. The flickering knots prove that nothing in the Crab Nebula is truly steady, and this creates a profound irony for the science that observes it. For decades, astronomers have treated the Crab as a cosmic lighthouse of a different kind, a standard candle in the high-energy sky. In the realms of X-rays and gamma rays, where bright, reliable sources are rare, the Crab's powerful and seemingly consistent glow became the go-to calibration tool. Scientists point their most advanced space telescopes at it to fine-tune their instruments, to measure the sensitivity of their detectors, and to compare the brightness of every other object they see. Its flux, its output of high-energy particles and light, was entered into textbooks as a fixed number, a constant against which all else could be measured. This reliance is the ultimate paradox. We have built our understanding of the violent universe upon a foundation that is itself cracking. The very object we use to define stability is the one showing us again and again that stability is an illusion. Those monstrous gamma-ray flares that double its brightness are not just fascinating anomalies, they are direct attacks on its credibility as a standard. Imagine if the kilogram weight kept in Paris, the official standard for mass, suddenly and unpredictably gained or lost 50 grams for a few hours at a time. Every scale calibrated against it would be thrown into chaos. The Crab's flares do exactly this to high-energy astronomy. A telescope observing a distant black hole during a Crab flare might miscalibrate, attributing the extra brightness to the black hole instead of its own flawed reference point. This forces scientists into a strange dance. They must now monitor the crab constantly, even as they use it as a baseline, watching for its tantrums so they can subtract its instability from their data. The meta-mystery is how this chaotic object ever earned such a trusted role. The answer lies in a matter of perspective and timescale. Compared to the flickering, erupting black holes and gamma-ray bursts that come and go in seconds, the crab, for most of the 20th century, appeared rock solid. Its variations were too subtle for older instruments to detect. It was the steadiest giant in a room full of strobe lights. Only with our modern, exquisitely sensitive telescopes have we seen its true, restless nature. Its tenure as a cosmic constant was a product of our own technological limitations. Now, its betrayal of that trust is a gift. It teaches a deeper lesson about the universe. There may be no such thing as a perfect standard candle in the high-energy cosmos, only objects that change too slowly for us to notice. The crab's refusal to sit still challenges us to build a more nuanced understanding, one that accounts for the inherent variability of even the most seemingly serene celestial engines. Our most trusted guide is leading us into uncertainty, and that is where the real discoveries begin. Our reliance on the crab's flickering light reveals a deeper truth that we are still learning to read its most basic language. That language is written in color, or more precisely, in the specific fingerprints of chemical elements. When astronomers break the nebula's light into a spectrum, they are not just seeing a rainbow. They are reading a forensic report from a stellar crime scene, a list of every element forged in the star's life and violent death. The data holds a startling chemical mystery. The abundances of key elements like helium, carbon, and oxygen are not evenly mixed throughout the glowing filaments. Instead, they appear in strange, lopsided ratios that vary from one part of the nebula to another. It is as if a master chef's ingredients were scattered not by recipe, but by a bomb blast, with vanilla concentrated in one corner and chocolate in another. These imbalances force us to reconstruct the final moments of the star and the explosion that tore it apart. The story begins deep inside the progenitor star, long before the supernova. For millions of years, it cooked lighter elements into heavier ones through nuclear fusion in its layered core. Helium fused into carbon, carbon into oxygen, and so on, creating an onion-like structure with the heaviest elements like iron at the very center. The supernova explosion was supposed to be the great mixer, blasting all these layers outward and churning them together into a more or less uniform soup. The spectroscopic maps tell us this mixing was incomplete, or perhaps something else happened. In some filaments, we see an overabundance of helium relative to hydrogen. This could be a pocket of the star's outer envelope, material that was never fully processed in the core and was blasted away relatively intact. Other regions glow brightly with the spectral lines of oxygen and carbon, but in ratios that don't match our clean theoretical models for nucleosynthesis. This suggests the explosion itself, with its unimaginable temperatures and pressures, may have triggered brief, runaway nuclear reactions in the expanding debris, creating fresh batches of elements on the fly. One particularly puzzling find is the strange behavior of certain elements like argon and sulfur. Their observed abundances in some knots are far higher than predicted, hinting at exotic nuclear processes we do not fully understand, processes that might only occur in the seconds during which a star's core collapses. Each filament, then, is not just a pretty tendril of gas. It is a time capsule, a frozen snapshot of a specific layer of the star or a specific instant of the explosion. The fact that they remain distinct, that the helium-rich zones and the oxygen-rich zones have not fully homogenized after 1,000 years, speaks to the incredible complexity of the blast. It was not a simple expanding fireball. It was a turbulent, chaotic maelstrom where some pockets of material were ejected cleanly while others were caught in vortices and shock waves that cooked them further. This chemical patchwork complicates a fundamental question: how much mass did the original star have? astronomers estimate stellar mass partly by the chemical yields of its supernova. If the elements are not evenly distributed, our single sample from Earth's viewpoint might be misleading. We might be overcounting the oxygen from one rich knot and undercounting the carbon from a faint, unseen filament. The nebula's spectrum is not a single clear sentence. It is a fragmented poem written in the language of atomic nuclei, and we are only now learning how to piece its stanzas together into a coherent story of the star that was. That chemical patchwork is a record of the star's violent end, but could the engine it left behind be writing new messages in a different, more explosive language? Among the most electrifying mysteries in modern astronomy are fast radio bursts, or FRBs. These are fleeting, ultra-powerful blasts of radio waves that originate from galaxies billions of light-years away, each one releasing more energy in a millisecond than our Sun does in 80 years. No FRB has ever been detected from the Crab Nebula itself, which is a crucial fact. Yet, the extreme physics churning within it has made the Crab a key testing ground for theories about what might cause these cosmic sirens. The connection is speculative but profoundly compelling. It hinges on a simple question: what natural object can possibly pack such staggering energy into such a brief flash? The prime suspects are neutron stars, and the Crab pulsar is the closest, most violent laboratory we have. One leading theory for FRBs involves starquakes on highly magnetized neutron stars called magnetas. A magnetar's crust, under unimaginable strain from a super-strong magnetic field, could suddenly crack. This catastrophic starquake would release a titanic wave of energy, shaking the magnetosphere and producing a brilliant radio burst. While the Crab pulsar is not a magnetar, it is a close, hyperactive relative. We have already seen its crust stutter with glitches. Could a much larger version of such an event, a super starquake, produce an FRB-like signal? Studying the smaller tremors in the Crab helps physicists model the limits of these dense stars, probing how much energy a crustal rupture could truly release. Another explosive idea focuses not on the star's surface but on the chaos surrounding it. This theory points to the nebula's magnetic field and its potential for sudden, catastrophic reconnection. As we discussed, when magnetic field lines snap and reconfigure, they can unleash incredible particle acceleration. Some models suggest that in especially dense, magnetized environments around a neutron star, a single, perfect magnetic reconnection event could channel energy into an extremely narrow, coherent beam of radio waves. For a millisecond, it would act like a cosmic laser or maser for radio frequencies. The turbulent, magnetized plasma of the Crab Nebula is exactly the kind of environment where such processes are constantly, if less powerfully, at work. We see smaller versions of this energy release in the gamma-ray flares. Could a different configuration produce a radio burst instead? Then there is the puzzle of the repeating FRBs. Some sources fire off multiple bursts over time. This rules out one-time cataclysms like a star collapsing into a black hole. It strongly suggests a persistent engine like a spinning neutron star. The Crab pulsar is the definition of a persistent engine ticking away for 1,000 years. Some models propose that repeating bursts could come from a neutron star with a messy, asteroid-like debris field. As chunks of rubble fall onto the star's surface, they could create bright, repeating flashes. While we see no such debris around the Crab, its environment shows how complex a pulsar's neighborhood can be, filled with clumps and knots of falling in material. So why has the Crab never produced an FRB? Distance and geometry offer possible answers. These bursts are likely beamed like the pulsar's own lighthouse emission. If its beam never sweeps across Earth, we would never see it. Also, the Crab's nebula itself might absorb or scatter such a signal before it could escape. Most importantly, the Crab pulsar might simply be the wrong type of neutron star. Its magnetic field strong, but not nearly strong enough to cross the threshold into the magnetar regime where the most violent bursts are thought to originate. This speculative link is not about finding an answer in the crab, but about using its extreme, observable physics to rule possibilities in or out. Every glitch, every flare, every shift in its magnetic field is a data point for the models trying to explain the universe's most powerful radio flashes. The Crab Nebula, in its furious activity, acts as a nearby stand-in, a controlled experiment we can watch in detail, helping us decipher signals that have traveled across billions of light-years of empty space. This restless motion extends all the way to the nebula's outermost frontier, where another layer of confusion awaits. For over a century, astronomers have been carefully measuring how fast the crab's shell is flying apart. By comparing Lord Ross's hand-drawn sketches from the 1800s to modern Hubble images, we can track individual filaments as they race outward. The simple expectation was that this expansion should be slowing down. After the initial supernova blast, the debris should be coasting, gradually decelerating as it plows into the thin gas of interstellar space. The historical measurements, however, hint at something far stranger. Some analyses suggest the outer filaments are not slowing down at all. If anything, they might even be maintaining their speed or, in certain directions, appearing to accelerate slightly. This is a direct challenge to the basic physics of an explosion in a vacuum. So what force could possibly be pushing on the outermost shell, keeping it moving fast 1,000 years after the detonation? The first possibility is an illusion of perspective, much like the superluminal wisps but on a much slower timescale. If the nebula is not a perfect sphere, but a complex, lumpy shape expanding into an uneven environment, our simple measurements from Earth could be misleading. Imagine a slightly lopsided balloon inflating. If you measure only the tip of one bulging lobe, it might seem to move faster than a flatter section, even though the internal pressure is the same. Our viewpoint, fixed from 6,500 light-years away, might be giving us a distorted sense of the true three-dimensional expansion. The second, and more thrilling, explanation brings the pulsar back into the spotlight. Its relentless wind does not just power the inner glow. That high-pressure bubble of particles and magnetic fields is constantly pushing outward against the inner surface of the expanding shell. It is like a tireless hand pressing on the inside of a balloon, preventing it from deflating as quickly as it should. This sustained internal pressure could, in theory, provide just enough extra oomph to keep the outer shell expanding at a nearly constant velocity, counteracting the drag from the interstellar medium. It would mean the pulsar's influence reaches far beyond the brilliant central cloud, its mechanical push felt at the very edges of the wreckage. A third, more exotic idea questions the explosion itself. Perhaps the supernova of 1054 was not a simple, symmetric blast. Some models for massive star deaths involved jets or highly directional outflows launched in the moments of core collapse. If the progenitor star fired such jets, the debris in those specific directions would have received an extra kick, a boost of energy that would make it expand faster and farther than the rest of the shell. What we interpret as a general acceleration might instead be the legacy of a lopsided, jet-driven explosion, its fingerprints still visible in the pattern of the fastest-moving filaments today. Pinpointing the truth requires more than just two snapshots in time. It demands a continuous, precise movie of the nebula's growth, tracking thousands of points over decades. Each tiny shift in a filament's position is a vote for one of these theories. If the acceleration is uniform, the pulsar wind is the likely culprit. If it is patchy and directional, we are likely seeing the ghostly imprint of the star's final, asymmetric death throes. This slow-motion puzzle reminds us that the crab is not a frozen fossil. It is a dynamic entity where the energy of the past explosion is still wrestling with the persistent power of its remnant, a battle for momentum that unfolds across light years and centuries. The nebula's relentless motion is not matched by a uniform voice. Tune a radio telescope to the crab, and you will hear a brilliant, crackling symphony of synchrotron radiation, the sound of electrons spiraling at near light speed. Yet within that brilliant chorus are pockets of profound silence. Specific filaments and broad regions emit far less radio noise than their surroundings, appearing as dark gaps in the radio map. This quiet is not an absence of material. We can often see the gas glowing in visible light. It is an absence of the specific process that makes the crab sing. For a nebula powered by a relentless particle accelerator, these silent zones are a glaring contradiction. They force us to ask what is missing or what has been switched off in these particular corners of the wreckage. Synchrotron radiation requires two ingredients: a healthy supply of ultra-fast electrons and a strong, organized magnetic field to whip them around. If a region is radio quiet, one or both of those ingredients must be lacking. Perhaps the magnetic field in these zones is peculiarly weak or tangled into a configuration that cannot efficiently accelerate particles. Think of a river generating hydroelectric power. It needs both a strong current and turbines in the right position. A silent zone might be a placid eddy where the magnetic current has dissipated, or where the field lines are oriented in such a chaotic knot that electrons simply slip through without being whipped into a radiating frenzy. The other possibility is a shortage of fuel. Maybe the pulsar's wind, that flood of high-energy particles, does not reach every part of the nebula evenly. There could be magnetic barriers or dense walls of slower-moving gas that deflect the wind, leaving certain filaments starved of the fresh, fast electrons needed to produce the radio glow. These regions would be like fertile fields cut off from the river's flow, left to lie fallow while the land downstream flourishes. This patchiness is a direct challenge to the simplest models of the crab, which often assume a relatively smooth, uniform injection of energy from the pulsar. The radio map tells a different story, one of a deeply uneven landscape. Energy distribution is lumpy, and magnetic topology is wildly variable from one filament to the next. A silent region might be a fossil, a pocket of the original star's ejector that has been largely bypassed by the pulsar's modern influence, preserving a quieter, older state. Or it could be a zone of magnetic reconnection that already happened, a place where the field lines snapped and released their energy in a burst we missed, leaving behind a calm, depleted aftermath. These quiet patches are as important as the bright ones. They are the control experiments in the nebula's chaotic laboratory, showing us what happens when the engine's key components are dialed down. By mapping exactly where the radio silence falls, astronomers can reverse engineer the invisible pathways of magnetic fields and particle flows, tracing where the pulsar's power goes and, more importantly, where it does not. In a structure defined by its brilliant emissions, the silent spaces speak volumes about all we still cannot see. That radio silence marks a boundary, but step outside the nebula's main body and another, far more ethereal layer comes into view. A delicate, ghostly skin of ultraviolet light envelops the entire structure. This is not the brilliant, chaotic glow of the inner filaments. Seen through the eyes of ultraviolet telescopes like NASA Galax, this outer skin appears as a faint, wispy network of its own, a lacy veil stretched over the violent machinery within. Its light is the signature of gas heated to temperatures of tens of thousands of degrees, a searing but thin atmosphere for the crab. The source of this heat is a fundamental question about the nebula's relationship with the space around it. Is this ultraviolet skin the mark of the nebula's forward shock, the leading edge of the explosion as it rams into the cold, quiet gas of interstellar space? When that supersonic wall of debris collides with even the sparse material between stars, it compresses and heats it violently, much like the bow wave of a ship glows as it pushes through water. That heated gas would then radiate its energy away in ultraviolet light, tracing the very outermost boundary of the expanding wreckage. This explanation paints a picture of the crab as a ship still plowing forward, its ultraviolet glow the fiery evidence of its journey. Yet there is a compelling alternative. This delicate skin might not be the product of the ancient explosion at all, but a modern creation of the pulsar wind. The pulsar's relentless outflow creates a high-pressure bubble inside the shell. That bubble must push outward, and where its pressure meets the inner surface of the slower-moving supernova debris, it creates a second internal shock front. This collision zone could also heat gas to ultraviolet-emitting temperatures. In this view, the ultraviolet filaments are not the outermost edge, but an inner lining, a shimmering interface where the power of the present-day engine meets the relics of the past. The structure of this ultraviolet emission offers clues. It is filamentary and incredibly intricate, suggesting a process shaped by magnetic fields and turbulence, not just a simple, smooth shock wave. Some of the most delicate strands appear to connect back to the inner nebula, as if the pulsar's influence is painting directly onto the inside of the cavity wall. Determining which process dominates is more than academic. If the ultraviolet light comes mostly from the forward shock, it tells us about the density and composition of the interstellar medium the crab is traveling through, mapping the emptiness it disturbs. If it is powered by the pulsar wind, it becomes a direct measure of how that wind is transferring its energy to the expanding shell, a key piece in understanding the nebula's long-term evolution. This luminous skin, so easily overlooked next to the brilliant core, is a critical boundary layer in a cosmic conversation, a whisper of heat that reveals whether the past explosion or the present engine is writing the final lines of this story. The shimmering skin of the crab is a map of its influence, but the engine at its heart is not content to sit still at the center of the map. The pulsar itself is on the move. Precise measurements from observatories like Hubble and Chandra reveal a startling fact. That city-sized sphere of pure neutron matter, the furious dynamo powering the entire nebula, is racing through its own wreckage at a blistering speed of about 1,500 kilometers per second. To put that in perspective, it is moving fast enough to travel from Earth to the Moon in under 5 minutes. This is not the gentle, uniform expansion of the nebula as a whole. This is a runaway, a bullet fired from the supernova blast that is now streaking through the cloud of its own making. Astronomers call this its proper motion, and it presents one of the most enduring puzzles in neutron-star physics, the mystery of the natal kick. How did the supernova explosion of 1054 impart such an incredible velocity to the dense stellar corpse it left behind? A star exploding is not supposed to launch its core like a cannonball. The prevailing image is of a symmetric blast, blowing the star's outer layers outward in all directions while the core collapses neatly into a neutron star at the dead center. The crab's pulsar speeding off to one side shatters that simple picture. It tells us the explosion was fundamentally lopsided, a cosmic detonation with a powerful directional bias. But what physical process could possibly skew a star's death so dramatically? One of the leading theories involves the most elusive particles in the universe, neutrinos. In the final, catastrophic milliseconds of a core collapse supernova, the forming neutron star is unimaginably hot, a cauldron of energy so intense that it floods the universe with more neutrinos than there are stars. These ghostly particles barely interact with matter, but in such stupendous numbers, even a tiny asymmetry in their emission could act like a rocket engine. If just 1% more neutrinos streamed out in one direction than in all others, the recoil could kick the newborn neutron star in the opposite direction at thousands of kilometers per second. It is a concept as elegant as it is difficult to prove, a rocket powered not by fire but by a silent storm of ghost particles. Another possibility reaches for a more tangible force, gravity. Could the progenitor star have had a binary companion? If the exploding star was in a tight orbit with another star or even a large planet, the sudden, violent loss of mass during the supernova could have unbalanced the gravitational dance. The neutron star might have been slingshotted away by the gravitational pull of its surviving partner, flung on its high-speed trajectory. The problem with this theory is the same as the search for a ghostly remnant core. We see no evidence of such a companion today. It might have been ejected in the other direction, or perhaps the kick was so powerful it completely severed the gravitational bond, leaving the pulsar to travel alone. A third, more exotic idea looks to the supernova engine itself. Some computer simulations suggest that the collapse does not proceed smoothly. Instabilities can cause the shock wave to stall and then restart in a violent, lopsided convulsion. Powerful jets of material might punch out in one direction while a corresponding recoil slams the proto-neutron-star the other way. In this scenario, the kick is not a gentle nudge but a brutal recoil from the star's own death throes, a final, asymmetric spasm that launched the core on its journey. The path of the pulsar, marked by a slight but measurable shift against the background nebula over years, is a permanent arrow pointing back to the moment of its birth. It is a fossilized record of imbalance, a clue that the chaos of a supernova is not just in the expanding debris, but woven into the very trajectory of the remnant it leaves behind. Every kilometer per second of that speed is a question about forces that lasted for less than a second, a billion years ago. The pulsar's high-speed journey through its own wreckage is mirrored by an even faster, invisible exodus. While the neutron-star races through space, its most energetic particles are fleeing the nebula entirely, leaving behind a ghostly signature of their escape. Far beyond the beautiful filaments we see in optical light, a faint but immense halo of the highest energy gamma rays ever detected envelops the entire structure. This is the teraelectronvolt or TeV gamma ray halo. To sense it, astronomers do not use ordinary telescopes. They employ ground-based arrays like Veritas and MAGIC, which detect not the gamma rays themselves, but the faint blue flashes of Cherenkov radiation produced when these gamma rays smash into Earth's upper atmosphere. The resulting map is startling. It shows a vast, diffuse glow of unimaginably energetic light stretching well beyond the familiar boundaries of the Crab Nebula. This halo presents a profound acceleration puzzle. The gamma rays are produced when ultra-relativistic particles, primarily electrons and positrons moving at almost the speed of light, collide with lower-energy photons from the cosmic microwave background, the leftover glow from the Big Bang. But there is a serious confinement problem. These particles are so energetic that they should not linger in one place. Their immense speed means they can travel across the entire halo region in a mere few years, yet the halo itself is tens of light years across and persists over centuries. If the particles are coming directly from the central pulsar, they should have streamed away into interstellar space long ago, leaving the region dark. The fact that we see a glowing halo means something is trapping them, corralling these frantic particles within this vast volume long enough for them to produce the TeV glow. Think of it like trying to contain fireflies in a stadium with all the doors wide open. The fireflies, representing the particles, would instantly escape. To see the stadium glow with their light, you would need invisible nets or barriers at every exit, gently bouncing them back inside. The TeV halo is evidence of such a cosmic barrier. The leading candidate is a magnetic trap. The interstellar medium around the Crab Nebula is not a perfect vacuum. It is threaded with a weak, galaxy-wide magnetic field. Theorists suggest that the pulsar's powerful wind, as it expands far beyond the visible nebula, can amplify and tangle this surrounding magnetic field, creating a turbulent maze. When the highest energy particles try to flee, they become trapped in this magnetic labyrinth, scattering off the tangled field lines and diffusing slowly outward rather than streaming away in a straight line. This process allows them to live long enough within the halo region to produce the TeV gamma rays we detect. The implications are staggering. The halo is a direct signpost that the Crab Nebula is a prolific source of cosmic rays, specifically electrons and positrons, injecting them into the galaxy. It acts as a natural particle accelerator and storage facility on a scale dwarfing the visible nebula. This vast, invisible reservoir of high-energy particles is a crucial piece of the nebula's total energy budget, a previously hidden component of its output. The size and brightness of the TV halo help astronomers measure the efficiency of this escape and trapping process, offering a unique natural experiment in how stellar remnants enrich the galaxy with energetic particles. It transforms our view of the Crab from a brilliant but isolated cloud into a central hub of activity whose influence paints the surrounding space with the highest energy light, a beacon whose true reach was only discovered by looking for the shadows it casts on our own atmosphere. That invisible halo of trapped particles is a testament to the pulsar's far-reaching influence, but the structure of its power much closer to home is even more intricate. Chandra's X-ray vision has peeled back another layer, revealing a ghostly double in the nebula's heart. Surrounding the pulsar, we already knew about the bright X-ray torus, that brilliant donut of high-energy particles. But nestled just inside it, Chandra detected a second, fainter ring, a delicate echo of the first. This is the double ring structure, and its presence complicates our picture of the pulsar's wind in a profound way. The bright outer torus is understood as a shock front, the place where the pulsar's ultra-fast wind slams into the slower-moving nebula and gets compressed and heated, glowing fiercely in X-rays. So what then is this inner ring? It cannot be another independent shock. One leading idea is that it represents a standing wave in the pulsar wind itself. Picture the pulsar as a rock dropped into a pond. The main circular wave rushing outward is the bright torus, but sometimes closer to the point of impact, you can see a second, smaller, concentric ripple that forms and holds its position. This inner X-ray ring could be a similar phenomenon, a stable ripple in the flow of the magnetized wind, created by some resonance or instability just before the wind crashes into the main shock. It is a fossilized imprint of the wind's complex internal structure. Another possibility points to the past. This faint ring could be the relic of a much more powerful, ancient outburst from the pulsar. Perhaps centuries ago, the pulsar experienced a hyperglitch or a magnetic reconnection event of unprecedented scale, blasting out a shell of material that expanded and then stalled, freezing into a permanent ring inside the modern torus. It would be a kind of cosmic scar, a reminder that the engine's fury has not always been at its current steady roar, or perhaps the explanation is geometric. The pulsar's wind may not be a smooth, uniform outflow. It could have a layered structure with different energies or particle densities streaming out at different latitudes. The inner ring might trace the boundary between two distinct layers within this structured wind, a contact discontinuity made visible by X-ray emission. Each explanation paints a different portrait of the pulsar's engine. A standing wave suggests a wind of exquisite dynamic complexity. A fossilized outburst tells a story of violent historical change. A layered wind implies a level of order we are only beginning to map. The fact that the ring is faint and so close to the dazzling central source makes it extraordinarily difficult to study in detail, its subtle light easily washed out by the brilliance around it. Yet its very existence is a crucial clue. It forces us to acknowledge that the zone between the pulsar's surface and the main shock is not an empty highway. It is a region rich with structure and history, where the raw power of the neutron-star begins to sculpt itself into the forms we see. This ghostly inner ring is a whisper from the engine's antechamber, a hint that even before its wind meets the nebula, it is already weaving patterns we are only starting to decipher. This ghostly inner ring is a structure of exquisite complexity, and the light that passes through it carries a hidden, spiraling message. The optical light from the nebula's heart does more than just shine. It vibrates with a specific orientation, a polarization that traces the invisible magnetic field lines, and that polarization is not static. It rotates with a period incredibly close to the pulsar's own 30 Hz spin. At first glance, this seems like a straightforward echo. The pulsar spins, its magnetic field rotates with it, and the polarization of the light it influences should spin in sync. But nature is rarely that simple. This optical polarization rotator is not a perfect lockstep signal. Its dance is messy, lagging, and full of subtle irregularities that reveal a far more turbulent reality between the pulsar and the nebula. The core of the mystery is geometry. The pulsar's magnetic field is not aligned with its spin axis. It is tilted, turning it into a wobbling cosmic lighthouse. As it spins, the orientation of the magnetic field in the wind zone changes, which in turn influences the preferred vibration direction or polarization of the light emitted by particles spiraling along those fields. So we should see that polarization angles sweep around in a circle, right? The problem is the vast distance between the pulsar and the region we are observing. The light we see in optical wavelengths does not come from right next to the neutron star. It is produced farther out in the turbulent zone where the pulsar wind is beginning to collide with itself and the nebula. By the time the magnetic signal from the pulsar's rotation propagates out to that region, it has been processed, scrambled, and delayed by the chaotic plasma it must travel through. Think of it like trying to conduct an orchestra from another room. You, the conductor, are the pulsar beating a steady 30 times per second rhythm. The musicians in the next room are the particles in the wind zone. They can hear your beat, but the walls muffle and distort the sound. Some musicians react instantly, others are slightly delayed, and the instruments themselves color the note. What emerges is a version of your rhythm, recognizable but imperfect, with a collective timing that lags behind your own precise movements. The rotating polarization angle is that collective musical response. It follows the pulsar's beat, but its period is not exactly 30 Hz, and its rotation is not perfectly smooth. These tiny discrepancies are gold dust for astrophysicists. They are direct measurements of the conditions in that inaccessible wind zone. The lag tells us about the speed and density of the outflow. The irregularities map the turbulence and shocks where the wind is first processed. By meticulously comparing the pulsar's pristine radio timing model to the messy optical polarization rotation, scientists can reverse engineer the properties of this violent intermediary region. This phenomenon transforms the nebula's light from a simple beacon into a sophisticated diagnostic tool. Each photon vibrating in a specific direction is a messenger that has journeyed through the pulsar's chaotic magnetic storm. The fact that we can detect this slow, majestic rotation at all, this grand sweep of polarized light keeping rough time with a city-sized spinning star 6,500 light-years away, is a triumph of observation. But the real story is in the imperfections, the slight stutters and delays in that rotation. They are the fingerprints of the nebula's inner workings, a slow-motion record written in vibrating light, detailing how raw power from a neutron star is shaped and tamed before it illuminates the cosmos. The light vibrating from the nebula's heart tells one story, but a colder, darker signature tells another. Deep within the infrared glow we discussed earlier, telescopes like Spitzer and now the James Webb have pinpointed specific, puzzling structures. They are not the brilliant filaments of hot gas. They are clumps and tendrils of something far more mundane, yet infinitely more mysterious: dust. This is not a uniform haze. These are distinct, unresolved knots and filaments of solid material, and they pose a direct challenge because their locations do not match up neatly with the glowing gas structures we see in optical light. It is as if you had a detailed map of a city's electrical grid, and then someone handed you a second map showing patches of moss growing on buildings, and the two maps refused to align. This disconnect forces a fundamental question about the very substance of the nebula. What is this dust made of, and where did it come from? The hunt for an answer splits into two radically different possibilities, each with profound implications. The first is a story of survival against impossible odds. This dust could be ancient, pre-existing material from the outer atmosphere of the progenitor star itself. In the final millennia of its life, as the massive star burned through its nuclear fuel, it would have blown a slow, dense wind of gas into space. In the cooler reaches of that wind, atoms could have clung together to form microscopic grains of carbon and silicate like soot forming in a candle's flame. Then the supernova blast wave arrived. The conventional wisdom said such a delicate structure, a cloud of dust motes, should have been utterly vaporized by the million-degree shock front, reduced back to individual atoms. Yet the infrared images suggest maybe, just maybe, some of these ancient grains endured. They were not destroyed, but merely swept up and heated by the expanding debris, and now they glow faintly with residual warmth. If true, this would be a staggering revelation. It would mean solid matter can survive one of the most violent events in the universe, carrying the direct mineral fingerprint of a star that died 1,000 years ago into the future. The second possibility is even more astonishing. It is a story of creation from chaos. This dust may not be a survivor, but a newborn. It could have formed entirely after the supernova, in the expanding, cooling wreckage itself. As the ejected gas from the explosion raced outward, it would have eventually cooled enough for atoms to begin sticking together again. In the dense, protected cores of some filaments, carbon, silicon, and iron atoms could have coalesced to form entirely new generations of dust grains. This process would be the universe's ultimate recycling program, taking the atoms forged in stellar fusion and a supernova, and using them to build the solid seeds for future planets and perhaps even life. The fact that the dust structures don't align with the gas filaments could be a clue to this origin. Perhaps dust only forms in specific environmental niches within the nebula, places where the temperature, density, and chemical mix are just right, creating an uneven, patchy distribution that our telescopes are only now resolving. Determining which story is true is not just about cataloging components. It strikes at the heart of a cosmic cycle. Are we looking at the last remnants of a dead star or the first building blocks of something new? The answer lies in the detailed spectrum of the infrared light, the specific chemical fingerprints the dust emits. Different materials form at different temperatures and under different conditions. If the dust is rich in certain types of carbon molecules, like polycyclic aromatic hydrocarbons, it might favor a post-explosion origin. If it shows signatures of crystalline silicates that require a long, quiet period to form, it might point to the pre-existing star. Every new observation from telescopes like JWST brings us closer to an answer, reading the mineral content of a cloud 6,500 light-years away. These cold, dark knots, so easy to overlook next to the nebula's brilliant light, may hold the secret to how death gives way to birth and how the ashes of one star become the clay for another. These cold knots of dust whisper one story of the nebula's composition, but to hear its full chemical confession, we must listen to its light in a far more precise way. This brings us to the realm of spectroscopy, where the Crab Nebula's glow is broken apart into a rainbow of individual colors, each one a barcode for a specific atom or ion. The resulting spectrum is not a few clean lines. It is a dense, bewildering forest. Thousands upon thousands of faint, narrow emission lines crowd together, a thicket of light signatures from ions of iron, nickel, oxygen, argon, and sulfur in various states of ionization. It is the spectral fingerprint of utter chaos, a complete inventory of the star's guts scattered and excited by the explosion. Each line is a tiny beacon announcing the presence and physical state of a specific element. The sheer density of this forest is the first clue to the nebula's incredible complexity. It tells us the debris is not a simple, homogeneous soup. It is a mad mosaic of different gas parcels, each with its own unique history of heating, cooling, and shock processing since the moment of the blast. Untangling this forest is the work of decades, a patient effort to identify every single line and trace it back to its source atom and the exact energy level transition that created it. Within that thick spectral forest, some lines shine with a special significance. They are called forbidden lines. The name is dramatic, but it refers to a quantum mechanical quirk. In an atom, electrons can jump between energy levels, emitting a photon of a very specific color when they do. Some jumps, however, are so statistically unlikely that under normal conditions on Earth, they almost never happen. In the high-density environment of a lab or a star's interior, an excited electron will almost always lose its energy through a collision with another particle or a more probable transition long before it can make this unlikely leap. These transitions are, for all practical purposes, forbidden, but the Crab Nebula is not a normal environment. Its filaments are incredibly tenuous, with densities millions of times lower than the air we breathe. Here, an excited ion can float for minutes, hours, or even years without a single collision. Given enough time, even the most improbable event can occur. In the deep vacuum of space, these forbidden transitions finally get their chance, emitting their distinct, faint glow. For astronomers, these lines are not a nuisance. They are a gift, a precise diagnostic tool. The relative strength of different forbidden lines from the same element acts like a cosmic thermometer and barometer. By measuring their ratios, scientists can calculate the exact temperature and density of the gas in a specific filament with an accuracy impossible to achieve any other way. This creates a powerful yet puzzling mapping exercise. By studying the forest of normal lines and the precise signatures of the forbidden ones, astronomers can create detailed charts of the nebula's physical conditions. They can produce maps that show not just where the gas is, but how hot it is and how densely packed, filament by filament. The picture that emerges is one of wild, unpredictable variation. Two neighboring tendrils of gas, seemingly identical in a visible light image, can have temperatures differing by thousands of degrees and densities that vary by an order of magnitude. One filament might be a relic of the star's inner core, still fiercely hot and rapidly expanding. The one right next to it might be a cooled, compressed ribbon from the outer envelope plowed up by a passing shock wave. The spectral forest is the record of this inequality, proving the supernova did not mix its ingredients smoothly. It was a turbulent blender that left some chunks nearly untouched and others vaporized and recondensed. Each forbidden line is a whisper from a tiny, isolated pocket of the nebula, telling us its very specific story of heat and loneliness. Together, they compose a chorus that sings not of uniformity, but of a beautiful, intricate disorder, a testament to the violence that could not erase the individual histories of the star's scattered remains. That spectral forest of light is a chemical map, but the shape of the spectrum itself holds a deeper secret about the particles creating it. Plot the crab's brilliance from the lowest radio waves to the highest gamma rays on a logarithmic graph, and you will not see a straight line. Instead, the curve makes a distinct, subtle bend. This is the cooling break, a specific frequency where the physics of the nebula's engine shifts gears. It is a fundamental signature of how the most energetic particles live and die within the magnetic storm. To understand it, picture two runners in a race through a field of mud. The first runner, representing a low-energy electron, moves slowly. The mud slows them down a little, but they can plod along for a long distance before exhausting their energy. The second runner is an ultra-high-energy electron, sprinting at nearly the speed of light. For them, the mud is a devastating obstacle. They lose their tremendous energy incredibly fast, slowing down after just a short, brilliant dash. In the nebula, the mud is synchrotron radiation itself. The faster an electron spirals around a magnetic field line, the more power it radiates away. This creates a critical threshold. Below a certain energy, electrons radiate slowly enough that they can travel across the nebula before cooling down. Above that energy, they lose their power in a blinding flash, confined to tiny regions near their acceleration sites. The cooling break is the frequency of light emitted by electrons right at that energy threshold. It marks the bend in the spectrum where the emission from the long-lived, low-energy runners gives way to the brief, fierce blaze of the sprinters. Its observed location is a direct probe of the nebula's magnetic field strength and the efficiency of its acceleration process. If the break is at a higher frequency than our models predict, it suggests a weaker magnetic field or more efficient acceleration, allowing electrons to reach higher energies before they burn out. If it is lower, it implies a stronger magnetic field that drains the sprinter's energy even faster. The cooling break is not just a line on a graph, it is a cosmic pressure gauge measuring the invisible forces that govern the lives of the nebula's most energetic inhabitants. Yet when we measure it, the data presents a puzzle. The break does not appear as sharp and clean as the simplest theories suggest. It is smeared, as if the mud in our analogy has a different consistency in different parts of the field. This blurring hints that the magnetic field strength or the acceleration process is not uniform throughout the nebula, a clue that leads directly to an even more profound distribution mystery. The smeared cooling break is a symptom of a deeper complexity in the nebula's heart. If the Crab's particle accelerator worked in one simple, perfect location, we would expect the energy distribution of its electrons to follow a clean, mathematical rule called a power law. Plotting it would yield a straight line on a log-log graph, but the data refuses to comply. The line is not straight. It has curves, bumps, and subtle changes in slope. This distorted distribution is a clear message. The particles powering the Crab Nebula are not all accelerated in the same way or in the same place. Instead, the nebula must contain multiple, distinct acceleration sites, each with its own personality and efficiency. Imagine a city's electricity coming not from one power plant but from several. You have a massive coal plant providing baseline power, a hydroelectric dam adding capacity during peak demand, and a scattering of solar farms contributing when the sun shines. The total power output is a complex blend from all these sources. The Crab Nebula's particle energy distribution is the cosmic equivalent of that blended grid. The pulsar's wind termination shock, where its outflow slams into the nebula, is the primary coal plant, the main accelerator, but other processes are adding their own streams of particles. The violent magnetic reconnection events that cause the gamma-ray flares are like sudden, powerful hydroelectric surges. Turbulent eddies and secondary shocks within the expanding wind could act like smaller solar farms, locally boosting particles to specific energies. Each of these sites imprints its own signature on the overall particle population. Some might produce a surplus of medium-energy electrons, creating a bump in the distribution. Others might be inefficient at producing the very highest energies, causing a steep drop-off. The result is a composite spectrum, a tangled record of every violent process occurring within the cloud. This complexity shatters the old, simple view of the Crab as a single, well-behaved engine. It reveals a hierarchical, messy reality where energy from the central pulsar is processed through a cascade of different mechanisms before finally escaping as light. The bent and bumpy spectrum is therefore the most honest portrait we have. It does not show a theoretical ideal. It shows the vibrant, chaotic, and multifaceted truth of a supernova remnant in action, a truth written in the twisted paths of countless electrons spiraling through a storm of their own making. The twisted paths of those electrons create a light show that flickers across every color, including those our eyes cannot see. The ultraviolet glow of the Crab Nebula is a restless, shifting signature. Far from being a steady output, its ultraviolet flux rises and falls on timescales ranging from days to years, a hidden rhythm in the high-energy heartbeat of the nebula. This variability is another crack in the facade of the Crab as a cosmic constant. It tells us the processes that heat the gas to tens of thousands of degrees, whether from shocks or the pulsar wind, are themselves inconstant. A slight strengthening of the pulsar's wind could pump more energy into the nebula's outer skin, brightening its UV glow for a period. Alternatively, the passage of a dense knot of gas through a shock front could cause a temporary spike in heating and ultraviolet emission. Each fluctuation is a clue, a real-time monitor of the energy sloshing around within the vast, chaotic cavity. Observing these changes requires patience and dedicated space telescopes, building a light curve, a graph of brightness over time. That looks less like a flat line and more like the erratic readings of a seismograph during a period of sustained tremors. This constant change sets the stage for one of the most tantalizing and controversial ideas in the nebula's history. Decades ago, while studying older radio telescope data, a few researchers noticed something almost unbelievable. The Crab's radio flux, its steady synchrotron hum, appeared to show a faint periodic dip that loosely correlated with the 11-year solar cycle. The suggestion was that activity on our own sun, 93 million miles away, might somehow be influencing our measurements of an object 6,500 light-years distant. The implications would be revolutionary, hinting at a previously unknown connection between stellar activity and interstellar propagation, a kind of cosmic interference spanning the galaxy. The sobering reality, however, is that such correlations are the most treacherous territory in observational science. The human brain is exquisitely wired to find patterns even when none exist. Given two independently variable datasets like solar activity and the Crab's radio output, it is statistically probable that you can find some time period where they appear to move in sync, purely by random chance. It is like listening to two different songs on separate radios. If you listen long enough, you will eventually hear a moment where the beats seem to match perfectly, but it is an illusion of timing, not a shared rhythm. Critics swiftly pointed out the immense physical hurdle. For the Sun to directly affect the Crab Nebula itself would require a mechanism that defies known physics, a signal or particle stream that not only travels that immense distance but then modulates a nebula's intrinsic power output. A more plausible, though still speculative, explanation would be a local effect. Perhaps changes in the solar wind alter the conditions in our own solar system's heliosphere, the bubble of space dominated by the Sun's influence. This could subtly affect how radio waves from the Crab pass through this local environment on their final journey to Earth, minutely changing the signal strength we record. But even this is considered a fringe idea, as the effect would be vanishingly small and incredibly difficult to disentangle from the Crab's own natural variability. The story of this correlation serves as a vital cautionary tale. It highlights the constant tension in astrophysics between the thrilling hunt for connection and the rigorous duty to rule out coincidence. The initial observation was not wrong, but its interpretation was likely a mirage, a pattern painted by noise and hope. It reminds us that the universe is full of parallel rhythms, the spin of a pulsar, the cycle of a star, the orbit of a planet. And their occasional, apparent alignment is a siren call we must approach with equal parts curiosity and profound skepticism. The true rhythms of the Crab are written in its own violent heart, not reflected in the quiet pulse of our nearby star. Zooming into the nebula's glowing tapestry reveals a universe of intricate detail. The filaments are not simple, smooth ribbons. Under Hubble's piercing gaze, they unravel into a breathtaking microstructure of braids, subthreads, and tangled knots, all woven on scales smaller than our solar system. This fine-scale braiding is a direct fossil of the explosion's primordial turbulence. As the expanding debris raced outward, it did not flow like syrup. It churned like a bomb blast in air, with faster streams shearing past slower ones, stretching and folding the material into these complex, ropey structures. The magnetic fields frozen into this plasma were stretched and amplified along with it, becoming the invisible threads that now help confine and shape these luminous tendrils. This braiding is nature's own high-energy physics experiment, a permanent record of fluid dynamics operating at relativistic speeds. Yet within this delicate lacework, a fierce and constant battle for balance is being waged. Each filament is a pressure vessel. On one side you have thermal pressure, the simple outward push of hot gas with temperatures reaching tens of thousands of degrees. This heat wants to make the filament expand, to dissipate into the surrounding void. Pushing back is the non-thermal pressure. This is the combined force of the magnetic field, which acts like a flexible cage, and the relativistic particles, those electrons and positrons spiraling at near light speed. These particles contribute a bizarre form of pressure. They are so energetic that they behave more like radiation than matter, exerting a relentless outward force. The existence of a sharp, defined filament means these opposing pressures have reached a precarious local truce. The magnetic field and particle pressure contain the hot gas, while the hot gas provides the material that sustains the magnetic turbulence and feeds the particle collisions. It is a self-regulating, dynamic equilibrium, but one that must be constantly managed. A slight increase in particle influx from the pulsar wind could overpressurize a filament, causing it to briefly puff up before perhaps reconfiguring its magnetic bonds. A cooling of the gas could weaken its outward push, allowing the magnetic field to contract the thread even tighter. This balance is what gives the crab its defined shape against the emptiness of space, a sculpture held together by invisible forces. The most dramatic evidence of this ongoing physical negotiation is found at the razor-sharp boundaries of the filaments themselves. These are not fuzzy, fading edges. They are ionization fronts, spectacularly thin transition zones where conditions change violently over a minuscule distance. On one side of this invisible wall, atoms are neutral, their electrons still bound to their nuclei. On the other side, they are ionized, stripped of their electrons by a flood of ultraviolet photons from the central pulsar and its shock-heated gas. Crossing this front is like stepping from a dark room into a searing spotlight. The moment a neutral atom is ionized, it begins to glow, emitting the specific colors of light that make the nebula visible. This creates those phenomenally crisp edges where brightness seems to switch on like a neon sign. These fronts are not static walls. They are propagating waves, slowly eating their way into the remaining pockets of cold, neutral debris left over from the supernova. Their speed and structure tell a precise story about the intensity of the ionizing radiation field and the density of the gas it is penetrating. A bright, sharply defined front indicates a powerful flood of UV light hitting a dense, resistant cloud. A more ragged, diffuse edge might suggest a weaker radiation field or a clumpier, more complex medium. Together, these three interwoven phenomena, the braided microstructure, the tense pressure balance, and the advancing ionization frontiers, define the living anatomy of the Crab Nebula. They transform it from a distant cloud into a dynamic ecosystem, where forces operating across scales from the subatomic to the interstellar collaborate in a delicate and violent dance to sculpt the light we see. The nebula's delicate structure is locked in a battle between forces that play out across wildly different clocks. Some of its transformations unfold with the patience of geology, while others flash by in a cosmic blink. On the grand year-to-year scale, the entire nebula breathes. Its overall synchrotron glow, that brilliant radio and optical hum powered by spiraling electrons, is not perfectly steady. Careful monitoring reveals a slow, persistent brightening over decades, a gradual increase in its total power output. This is not the sudden flare of gamma rays, but a deep, systemic change, like a power plant slowly ramping up its generators. The cause is almost certainly a large-scale evolution in the pulsar-wind nebula itself. As the pulsar's fierce wind continues to inflate its magnetic bubble inside the expanding shell, the shock fronts where this wind terminates may be slowly changing shape. A slight shift in the balance of pressure could cause the shock to become more efficient at accelerating particles, injecting more high-energy electrons into the system and brightening the entire nebula's glow. Alternatively, the nebula might be expanding into a slightly denser patch of the interstellar medium, causing more material to be swept up and heated, adding its own contribution to the total light. These year-scale variations are the long-term management of the estate, the slow adjustment of the entire engine's throttle. In stark contrast, other parts of the nebula live in a state of frenetic, day-to-day panic. Zoom in on a single knot, one of those dense beads of gas in the filaments, and you can watch it flicker like a candle in a draft. Its brightness can change by 10% or more in just 24 hours, its shape warping and pulsing as if alive. This is not a reflection of the pulsar's spin, which is 30 times a second, but something far more unstable. These day-scale flickers point to highly localized, violent processes. One knot might be experiencing a miniature magnetic reconnection event right inside it, a tiny snap of field lines that injects a burst of energy, causing it to brighten before the energy dissipates. Another might be a turbulent eddy in the plasma flow, where density and pressure are constantly sloshing around, leading to rapid changes in how much light it emits. It is like watching foam on a raging river. The river itself, the large-scale flow, changes slowly, but an individual bubble in the foam forms, pops, and reforms in an instant. The day-scale flickering proves that the nebula is not just a large, slow-changing cloud. It is a hive of microscopic instability, where even the tiniest structures are caught in a storm of change, telling a story of illumination and chaos that unfolds not over centuries but over days. These rapid flickers and slow breaths are the nebula's visible language, but some of its most important messages are written in silence. Three profound mysteries come not from what we see, but from what we do not. These are the non-detections, the missing signals that constrain our imagination just as powerfully as any brilliant flare. The first absence is found in the nebula's X-ray spectrum. When a massive star explodes, it is expected to forge huge amounts of iron in its final moments and scatter it into the expanding debris. This iron, heated to millions of degrees, should announce its presence with a brilliant, unmistakable fingerprint in the X-ray spectrum called the iron K emission line. It is a specific color of X-ray light that acts as a direct broadcast from one of the universe's heaviest elements. In the Crab Nebula, this line is startlingly faint. The iron is there, but in far lower abundance than our models for a core collapse supernova predict. This quiet signal forces a re-evaluation of the star that died. It suggests the progenitor may have been somewhat lighter than we thought, or that its internal fusion processes were unusual, leaving it with a smaller iron core at the time of death. Alternatively, the explosion mechanism itself might have been less efficient at producing iron, or perhaps much of the iron that was created fell back onto the nascent neutron star, locked away forever from our view. This missing line is a chemical constraint, a clue that the ingredients for this cosmic explosion were not the standard recipe. The second great silence is even more ghostly. The Crab pulsar is a furious particle accelerator, and many models suggest that the processes creating its highest energy gamma rays should also produce a detectable flux of high-energy neutrinos. These nearly massless particles, which fly through planets like ghosts, are the perfect messengers from the heart of the most violent environments. Yet, despite dedicated searches by massive telescopes like IceCube buried deep in the Antarctic ice, the Crab Nebula has not sung in neutrinos. It remains a stubbornly quiet source. This non-detection is not a failure. It is a critical boundary. It tells physicists that their models for how particles are accelerated to petaelectron-volt energies within the nebula must be wrong or at least incomplete. If the gamma rays are produced primarily by electrons colliding with light, a process that does not create neutrinos, then the silence makes sense. but if protons were being accelerated and colliding within the nebula, they should produce both gamma rays and neutrinos. The fact that we see only the gamma rays suggests the Crab's hidden accelerator may be an electron-dominated machine, ruling out entire classes of theoretical models. It forces us to listen more carefully to what the light is already telling us. The third profound quiet comes from the fabric of spacetime itself. The Crab pulsar, with its furious spin and occasional glitches, should be a source of continuous gravitational waves. If its surface is not perfectly smooth, if it has even a tiny mountain, a mere centimeter-high deformation on its incredibly dense crust, the rapid rotation would create a persistent ripple in spacetime. Furthermore, a large starquake or a major glitch could produce a burst of gravitational waves. Observatories like LIGO and Virgo listen for these cosmic tremors. To date, they have heard nothing from the Crab. This silence is an exquisite measurement. It places an upper limit on the size of any mountain on the neutron star's surface, constraining it to be less than a few millimeters tall. That is an astonishing degree of smoothness for an object born from chaos. It also tells us that the internal rearrangements during its glitches, while dramatic to us, are not violent enough in terms of mass movement to significantly shake spacetime. Each of these three silences, the missing X-ray line, the absent neutrino stream, and the still gravitational field, is a form of data. They are the universe telling us what is not happening, drawing boundaries around the possible. In a nebula so full of brilliant, noisy light, these quiet absences are the whispers that guide us toward a truer, more complete understanding of the violent and elegant physics at play. Those profound silences in our modern data are balanced by a chorus of voices from the ancient world. The Crab Nebula is unique because we know precisely when its story began. In the early summer of the year 1054, a new star blazed into existence in the constellation of Taurus, witnessed and recorded by astronomers across the globe. These are not just historical footnotes, they are the first data points in a 1,000-year-long observation campaign. Chinese court astronomers, meticulous in their record-keeping, described it as a guest star visible in the eastern sky. Their texts note it was as bright as Jupiter, and astonishingly, it remained visible in broad daylight for 23 consecutive days. At night, it shone with a piercing, unmistakable light for nearly 2 full years before finally fading from view. Japanese observers saw it too, calling it a great guest star, and records from the Islamic world, though more sparse, also mention the sudden celestial visitor. There are even tantalizing hints from the ancestral Puebloan people in the American Southwest. A pictograph at what is now White Mesa, Arizona, shows a crescent moon with a large star very close to it. The moon's phase matches the position recorded by the Chinese on the morning of July 5, 1054, when the crescent sat just 2 degrees from the supernova's location. This convergence of global testimony gives the Crab a birth certificate, a precise moment in time that anchors all our studies. Yet these ancient records are not without their own puzzles. The discrepancies are subtle but telling. While the Chinese notes are incredibly detailed, other records vary on how long the star was visible during the day. Some suggest it was only for a few weeks, others imply a shorter period. This could be due to differences in local atmospheric conditions, the clarity of the observer's sky, or even the subjective judgment of what constituted daytime visibility. Was it truly as bright as Venus or merely like Jupiter? These small variations matter because they help astronomers estimate the supernova's absolute brightness, its peak luminosity. That number is crucial for working backwards to understand the star that exploded. The consistent thread across all cultures is the sense of awe. This was not a faint, curious speck. It was a world-altering event, a brilliant, lingering anomaly that challenged the very idea of a fixed and unchanging heavens. It left a cultural and scientific imprint so deep that we are still deciphering it today. This historical anchor allows us to play cosmic detective to perform stellar archaeology on the star that died. We know the when and the where. The question is, what was it? By studying the chemical composition and dynamics of the expanding nebula, astronomers can reconstruct the progenitor. The evidence points overwhelmingly to a massive star, one many times heavier than our own Sun. The sheer amount of energy needed to create the expanding cloud we see and to power the pulsar within it demands a giant. The abundance of elements like helium, carbon, and oxygen in the filaments suggests it was well along in its fusion cycle, having burned through the hydrogen in its core. Most experts believe it was a star between 8 and 12 times the mass of the Sun. At the upper end of that range, its life would have been a short, brilliant blaze of only a few tens of millions of years before its core ran out of fuel and collapsed. But the exact details spark debate. Was it a solitary giant, or did it have a companion star? The pulsar's high-speed kick suggests a lopsided explosion, which could hint at a binary partner that gravitationally disrupted the collapse. Was it a red supergiant, a vast, bloated sphere, or a more compact blue giant? The structure of the nebula's shell provides clues. Some models suggest the relatively confined shape of the crab indicates the progenitor star had shed much of its outer hydrogen envelope before the explosion, leaving a more compact Wolf-Rayet-type star. This would mean the beautiful filaments we see are not the star's entire bulk, but mainly its processed inner layers. The environment adds another layer. The nebula is expanding into a region of space that seems surprisingly low in density, suggesting the star's own stellar winds had already cleared out a large cavity around it long before the final cataclysm. This stellar archaeology, piecing together a life from the fragments of its death, turns the crab from a mere object into a biography. Every knot of gas, every ratio of elements, is a chapter in the story of a giant whose final act was so brilliant it was seen by human eyes a millennium ago, and whose remains continue to challenge everything we think we know about the lives and deaths of stars. The star's own winds may have cleared a path, but the nebula still journeys through a galaxy full of ghosts. Its interaction with the surrounding interstellar medium is a quiet, ongoing conversation that shapes its evolution. Is the crab plowing into a uniform void, or is it encountering a complex, lumpy landscape of ancient gas and dust? The answer lies in the subtle distortions of its outer shell. Observations of that faint, ultraviolet skin and the outermost radio filaments show they are not perfectly smooth or spherical. There are indentations, bright rims, and areas where the expansion seems slightly slower. These are the fingerprints of an uneven environment. It suggests the nebula is expanding into a region that is not empty, but filled with a very tenuous, patchy interstellar medium. Think of a snowplow moving down a street after a light, drifting snowfall. Where the snow has gathered into small banks, the plow's blade meets more resistance, its path slowing and its shape deforming slightly around the obstacle. The crab's forward shock is that cosmic plow, and the subtle bumps in its halo are the evidence of the gentle banks of interstellar material it is pushing aside. This interaction is crucial for understanding the nebula's future. A denser, more uniform medium would slow the expansion dramatically, compressing the shell and heating it further. The patchy, thin medium it seems to inhabit allows it to maintain much of its speed, preserving its delicate filamentary structure for millennia to come. Yet there is a faster traveler within this cloud, and its journey creates an even more elusive structure. The pulsar, racing through the nebula's interior at over 1,000 kilometers per second, is also moving through the local interstellar medium. Any object moving supersonically through a medium, whether a boat through water or a star through space, creates a bow wave ahead of it. For the crab pulsar, this should manifest as a bow shock, a region where the pulsar's fierce magnetized wind slams directly into the pristine interstellar gas. This collision would be a site of tremendous particle acceleration and heating, potentially glowing in X-rays or ultraviolet light. The hunt for this bow shock, however, has turned up frustratingly little. It should be there, a faint crescent-shaped glow ahead of the speeding neutron star, but our telescopes struggle to pick it out from the brilliant background of the nebula itself. Its non-detection or extreme faintness is its own kind of clue. It tells us that the local interstellar medium into which the pulsar is moving must be extraordinarily thin, perhaps even thinner than the average galactic void. A bow shock needs something to push against. If the pulsar is racing through a near-perfect vacuum, its wind might simply stream away unimpeded, failing to create that bright, compressed wall of emission. Alternatively, the geometry might be working against us. The bow shock's emission could be spread over a large, diffuse area, making its surface brightness too low for our current instruments to discern. Or perhaps the pulsar's wind is so dominated by magnetic pressure that it creates a more elongated, comet-like tail rather than a classic bow wave, directing the emission in a way we are not looking for. Finding this ghostly structure would be a triumph. It would give us a direct measure of the density and pressure of the interstellar medium in this specific region of the galaxy, taken from a moving probe. It would also show us the moment the pulsar's influence truly ends, where its private storm finally dissipates into the calm of galactic space. For now, its absence is a quiet reminder that even our most dynamic cosmic engines move through a universe that is, for the most part, profound and empty silence. That profound silence surrounding the speeding pulsar is a testament to the emptiness it travels through, but within the star itself, a far more consequential quiet is taking place. The very source of the nebula's power is slowly, inevitably fading. At the heart of the Crab's fury lies one of the strongest magnetic fields in the known universe, 1 trillion times more powerful than Earth. This field is the dynamo, the invisible engine that converts the pulsar's rotational energy into the particle wind that lights up the nebula, but such a field cannot last forever. Theoretical physics tells us it must decay, its immense strength slowly leaking away over millennia. The critical question is how fast. Measuring the magnetic field decay rate is one of the great challenges in neutron-star science, and the Crab pulsar is our most important laboratory. We cannot stick a probe into it. Instead, we must infer the field's strength indirectly by watching how the pulsar spins down. The connection is direct. A stronger magnetic field acts like a more powerful brake, grabbing the interstellar medium and radiating energy away more efficiently, causing the pulsar to slow its rotation faster. A weaker field applies less braking, leading to a gentler spin down. By meticulously tracking the pulsar's rotation over decades, we can work backwards to estimate the current field strength, and by comparing it to models of its birth, guess at how quickly it is fading. The data paints a picture of astonishing stability. The decay appears to be incredibly slow, suggesting the magnetic field is locked deep within the neutron star's superfluid core, protected by the star's incredible density. It might take tens of millions of years for its power to have. This slow decay has a profound implication for the Crab Nebula's future. It means the central engine will keep running at nearly its current ferocious pace for an astronomically long time. The beautiful filaments will eventually dissipate, but the pulsar-wind nebula, that brilliant central glow, will persist as a dominant source of high-energy light long after the supernova shell has faded from view. The pulsar is not just a remnant, it is a legacy object destined to outshine its own wreckage. This gradual spin down is the master clock for the entire system. Every single second, the Crab pulsar's rotation period increases by about 38 nanoseconds. It is an imperceptible change on human timescales, but over a year, that tiny slowdown adds up to a full extra millisecond per rotation. This steady braking is the ultimate source of the nebula's brilliance. The math is elegant and awe-inspiring. The rotational energy the pulsar loses as it slows down is precisely equal to the total power output of the entire Crab Nebula across all wavelengths of light, from radio waves to gamma rays. It is a perfect cosmic ledger. The energy does not vanish. It is transferred via the pulsar's wind and magnetic field into the nebula, where it accelerates particles and fuels the luminous glow we see. This correlation is one of the cleanest in all of astrophysics, a direct line from the spin of a city-sized star to the illumination of a cloud 10 light-years across. Yet within this precise relationship there are tiny, telling stutters. The spin down is not perfectly smooth. After accounting for the steady deceleration and the sudden glitches, a residual jitter remains. The pulsar's slowdown rate itself varies by a fraction of a percent over months and years. It is as if the brake pedal on this cosmic engine is being pressed with a subtly fluctuating pressure. These irregularities are the spin-down enigma. They hint at processes deep within the neutron star's interior that we can only theorize about. One possibility involves the superfluid core. This frictionless quantum fluid is thought to rotate at a constant rate, while the solid crust above it spins down due to magnetic braking. The two components are loosely coupled by the pinning of microscopic vortices. If this coupling changes even slightly, it could alter the efficiency with which rotational energy is extracted from the core, causing the observed spin-down rate to waver. Another idea points to the magnetosphere, the complex zone of magnetic fields and plasma surrounding the star. Small changes in the structure of this magnetosphere, perhaps driven by bursts of particle creation or shifts in current, could change how effectively it radiates energy, thus varying the braking torque on the pulsar itself. Each tiny irregularity in the spin-down is a message from a hidden realm. They tell us that the neutron star is not a simple, rigid flywheel winding down. It is a deeply complex object with interior layers and external fields in a constant, dynamic negotiation. The energy that flows from its core to light up the nebula does not travel a smooth pipeline. It passes through a storm of quantum weirdness and magnetic violence, and the faint tremors in its steady slowdown are our only clues to the turbulence within. The pulsar's steady spin-down feeds a nebula that glows with a deceptive geometry. In the brilliant X-ray light, the heart of the crab appears as a compact, vibrant torus, a whirlpool of high-energy particles. But this compact size hides a fundamental tension, a mismatch between scale and power. The electrons producing this fierce X-ray glow possess truly staggering energies. According to the basic physics of synchrotron radiation, such ultra-high-energy electrons should not be able to travel far from where they are accelerated. They radiate away their power in a blindingly short, brilliant flash, like a match struck in a vacuum that burns out in an instant. If that is true, the X-ray nebula should be incredibly small, confined to a tight region immediately around the pulsar's wind shock. Yet, the X-ray torus we observe, while compact, is still far larger than that theoretical limit allows. It is as if you lit a match and saw its glow illuminate an entire room, defying the natural reach of its flame. This is the synchrotron nebula-size energy paradox. How do these electrons, which should cool and fade in a tiny zone, manage to paint such a relatively large structure with their light? The resolution points to a dynamic and continuous process. The electrons are not making a single journey. They are being constantly re-accelerated. The pulsar's wind termination shock is not a one-time barrier but a turbulent, living surface. As electrons stream away from it, they lose energy and begin to fade, but the chaotic magnetic fields and secondary shocks within the nebula can catch them and give them another kick, boosting them back up to high energies. This process of diffusive re-acceleration allows the electrons to travel farther while still shining brightly in X-rays, inflating the observed size of the nebula. It is less like a single match and more like a chain of flares, each one lit as the previous one dims, carrying the light deeper into the cloud. The precise size of the X-ray nebula, therefore, becomes a direct measure of the efficiency and reach of this invisible re-acceleration network, a map of where the pulsar's fury is still actively stirring the pot. That same population of hyper-energetic electrons does more than just emit their own light, they hijack it. The very synchrotron photons they produce, the optical and X-ray glow that fills the nebula, become fuel for an even more extreme transformation. This is the realm of inverse Compton scattering, a particle physics dance that powers the Crab's highest energy gamma rays. Picture a slow-moving photon, a tiny packet of visible light drifting through the nebula. Now imagine a high-energy electron moving at almost the speed of light, screaming past it. In a violent collision, the electron can transfer a huge amount of its own kinetic energy to the lowly photon. The photon is not absorbed, it is catapulted upward in energy, transformed from a particle of visible light or soft X-rays into a monstrous gamma-ray photon. It is the cosmic equivalent of a ping-pong ball being struck by a speeding bullet. The ball is not destroyed, it is blasted away with impossible velocity. In the Crab, this process is profoundly self-contained. The nebula's own synchrotron photons serve as the target, and its own ultra-relativistic electrons act as the hammers. This creates a feedback loop where the nebula's lower energy output is recycled into its highest energy signature. Modeling this process is a delicate balancing act for astrophysicists. To accurately predict the gamma-ray flux we observe, they must have a perfect understanding of the density of both the target photon field and the hammering electrons at every point in the nebula. A slight overestimate in the number of electrons leads to a predicted gamma-ray glow far brighter than what we see. An error in mapping the synchrotron light leads to a mismatch in the spectrum. The fact that our models can roughly match the observations is a triumph, proving we understand the broad strokes of this energetic chain. But the persistent discrepancies, the subtle mismatches between prediction and reality, are the clues that our map of the nebula's interior is still incomplete. They hint at hidden zones where the photon density is higher, or where the electron energy distribution takes an unexpected turn. Every gamma-ray photon detected from the Crab is therefore a messenger twice over, first born as synchrotron light, then reborn through a violent collision, carrying within it a coded record of the invisible storms through which it has traveled. The very heart of the Crab Nebula is a place of impossible symmetry forged from chaos. At its center, the pulsar acts as a cosmic blowtorch, firing a hurricane of particles and magnetic fields outward at nearly the speed of light. This is the pulsar-wind, a torrent so powerful it would vaporize any planet in an instant. But this wind does not stream into empty space forever. It travels outward only until it smashes headlong into the slower-moving shell of supernova debris expanding around it. The collision point is a wall of pure violence called the wind termination shock. It is here, at this invisible boundary, where the raw fury of the pulsar is first tamed and transformed into the nebula's brilliant glow. The shock is not a simple, static barrier. It is a dynamic, rippling surface where the orderly wind is abruptly slowed, compressed, and heated. As particles cross this shock front, they are thrown into a frenzy, gaining tremendous energy. This is the nebula's primary particle accelerator, the place where electrons are first whipped up to nearly the speed of light and sent spiraling into the magnetic maelstrom, beginning their journey to become the synchrotron light we see. Yet the exact shape and location of this critical shock are still debated. Is it a smooth sphere, or is it rippled and distorted by instabilities? Pinpointing it is like trying to see the exact moment a river becomes a waterfall from miles away, a crucial transition hidden in a blur of motion and spray. What emerges from that chaotic shock, however, is a structure of breathtaking order. In X-ray and radio images, the nebula's core reveals a perfect geometric duality. Encircling the pulsar's equator is a brilliant, luminous torus, a donut-shaped ring of high-energy particles, and shooting out from the pulsar's poles, perpendicular to this ring, are two powerful jets like searchlights beaming into the depths of space. This is the iconic jet torus structure, a portrait of symmetry that seems utterly at odds with the random violence of a supernova explosion. How can such a clean, almost engineered shape arise from a star's catastrophic death? The answer lies in the anatomy of the pulsar itself. The neutron-star is an oblique rotator, meaning its magnetic poles are not aligned with its axis of spin. As it whirls, its intense magnetic field is dragged around like a colossal, spinning lighthouse magnet. This configuration focuses the pulsar wind, channeling it most powerfully along the open magnetic field lines near the poles, creating the focused jets. Meanwhile, the wind flowing out along the equatorial plane is denser but slower, and it piles up against the surrounding nebula to form the glowing torus. It is a natural consequence of physics, but its clarity is staggering. We are witnessing the invisible architecture of a magnetic field, painted across light years by obedient streams of high-energy particles. This perfect geometry raises a deeper question about the explosion itself. Did the star's collapse naturally impart this spin and magnetic alignment, or was the system somehow preset to create this beautiful, balanced outcome? The jet torus structure is more than a pretty picture. It is a frozen diagram of the fundamental forces governing the most energetic objects in our universe, a reminder that even in chaos, the laws of physics can write with a surprisingly steady hand. That perfect jet torus symmetry is only the surface of a far more tangled magnetic reality. To peer deeper, astronomers use a subtle but powerful trick of physics, the Faraday rotation. Imagine a beam of polarized radio waves, its light vibrating in a single plane, traveling from a distant source through the emptiness of space. If that beam passes through a cloud of magnetized plasma on its way to us, something remarkable happens. The magnetic field within that cloud will slowly rotate the plane of polarization, like an invisible hand twisting a dial. The amount of this Faraday rotation depends on two things: the strength of the magnetic field along our line of sight and the density of electrons in the plasma. By measuring how much the polarization of the Crab's radio waves is twisted at different frequencies, scientists can create a three-dimensional map of the nebula's internal magnetic environment. It is a non-invasive scan, using the nebula's own radio whisper to diagnose the invisible forces within. The resulting maps are anything but simple. They reveal a stunningly complex and variable magnetic landscape. The Faraday rotation is not uniform. It changes dramatically from one filament to the next, and even across a single filament. One region might show a strong, positive rotation, indicating a magnetic field pointed mostly toward us. Right beside it, another knot shows a negative rotation, a field pointed mostly away. This patchwork quilt of magnetic directions is the true state of the nebula's soul. It tells us the ordered toroidal field is just the background hum. Superimposed on it is a chaotic, local turbulence where magnetic fields are tangled, reversed, and folded by 1,000 years of violent motion. These variations are the scars of ancient shocks and the fingerprints of ongoing instability. A magnetic fingerprint proving the nebula is still dynamically rearranging itself from the inside out. This complex twisting finds its origin in the very engine of the system. The pulsar wind does not blow with a steady, even breath. Because the pulsar is a spinning oblique rotator, its wind is not a smooth flow but a rotating, spiral pattern, like water spraying from a spinning garden sprinkler. This rotating wind carries the pulsar's magnetic field with it, and as it expands outward, it drags and shears the field lines embedded in the nebula's plasma. The result is a gradual twisting of the entire magnetic architecture. Think of it as a potter spinning clay on a wheel. The central pulsar is the spinning wheel. The magnetized plasma of the nebula is the clay. As the wheel turns, it imparts a rotational force, twisting and stretching the material into a spiral form. Evidence for this large-scale twist is found in the polarization patterns themselves. The angle of polarization does not just point neatly around the torus, it often shows a systematic sweep, a gradual change in orientation that traces the imprint of this rotational drag. This adds a profound layer of dynamism to our understanding. The magnetic field is not a fossil frozen in place at the moment of the supernova. It is a living structure constantly being kneaded and wound by the relentless rotational energy of the pulsar. The beautiful filaments we see are not just passively illuminated by this field. They are active participants, their gas trapped and shaped by these twisting lines of force. The combination of the small-scale Faraday rotation variations and the large-scale magnetic twisting paints a complete and daunting picture. It shows a system where magnetic order and chaos exist in a permanent, violent embrace. The pulsar strives to impose its clean, rotating order, while the inherent turbulence of the expanding debris fights back, creating pockets of reversal and tangles. This magnetic dialogue is what ultimately shapes the nebula's glow, confines its particles, and dictates how its incredible energy will slowly dissipate into the galaxy. Every subtle twist in a radio wave's journey to Earth is a coded message about this ancient struggle, a struggle that continues to sculpt the heart of the crab. The magnetic dialogue that shapes the nebula's glow also leaves its mark on the coldest, most fragile components of the wreckage. Deep within the infrared haze, where telescopes sense the gentle warmth of solid matter, lies another layer of contradiction. Detailed maps from observatories like the Spitzer Space Telescope reveal that the dust scattered throughout the crab is not all the same temperature. While most of it is bitterly cold, just a few tens of degrees above absolute zero, there are distinct pockets where the dust is surprisingly warm, even hot by cosmic standards, reaching hundreds of degrees. This is the dust temperature puzzle. In an environment flooded with deadly radiation and searing particle winds, how can any solid grain stay cool, let alone warm up in such an uneven way? The answer is a story of location and shelter. The coldest dust likely resides in the densest, most shielded cores of filaments, far from the direct glare of the pulsar. It is warmed only by the faint, diffuse starlight that permeates the nebula, but the warmer patches present a challenge. They cannot be heated by the general synchrotron glow alone. That light is not efficient at warming solid grains. Something more intense and localized must be cooking them. One compelling suspect is the bombardment of low-energy electrons. While we often focus on the fastest particles that make X-rays, a vast population of slower, less energetic electrons also fills the nebula. When these particles slam into a dust grain, they deposit their kinetic energy directly as heat, like sandblasting a stone until it glows. A dense knot of gas could act as a trap for these particles, creating a localized hotspot where dust grains are continually sandblasted to higher temperatures. Another possibility points to the violent but brief energy of magnetic reconnection events. If a reconnection site occurs near a cloud of dust, the sudden flash of energy could heat the grains in a flash before the region cools again. The uneven temperature map, then, is not just a thermal chart. It is an indirect map of where the nebula's less glamorous but equally important low-energy processes are playing out, highlighting shelters and battlegrounds invisible to other wavelengths. This search for fragile components leads to an even more elusive quarry, one that would rewrite our understanding of the nebula's chemistry. Astronomers are engaged in a meticulous hunt for the signature of molecular hydrogen, known as H2, within the crab. This is the most basic molecule in the universe, two hydrogen atoms bound together. Finding it here would be nothing short of astonishing. The interior of a supernova remnant is considered the ultimate hostile environment for molecule formation. It is flooded with ultraviolet photons and X-rays energetic enough to tear molecules apart, and full of fast-moving particles that smash into any tentative atomic bonds. It is like trying to build a house of cards in the middle of a hurricane, yet some faint, puzzling features in the infrared spectrum hint that the impossible might be happening. Certain wavelengths of light appear slightly brighter than expected, aligning with the places where molecular hydrogen, if it were somehow surviving, would emit its telltale glow. So how could H2 possibly exist? The only way is through extreme shelter, deep inside the densest, coldest knots of gas, where the outer layers of material act as a thick radiation shield. A tiny, protected cavity might exist. In this shadowed refuge, hydrogen atoms could occasionally meet and bond, forming fragile molecules that emit their faint infrared signal before being destroyed. Detecting it conclusively would be a landmark discovery. It would mean that even in the most violent stellar aftermaths, nature finds a way to begin the slow, delicate work of chemistry, creating the basic building blocks for more complex structures in the shadows of the apocalypse. It would transform the crab from a purely destructive force into a potential nursery for the raw materials of future worlds. The nebula's intricate chemistry and hidden warmth are just pieces in a much larger accounting problem. After exploring 50 strange phenomena, from flickering knots to ghostly magnetic fields, we are left with one final, overarching question: does the cosmic ledger actually balance? This is the grand mystery of the crab's total energy budget. We can measure with exquisite precision the energy pouring out of the nebula across every wavelength, from the faintest radio whisper to the most violent gamma-ray scream. We can also measure with equal precision the energy being fed into the system, the rotational power lost by the pulsar as it gradually spins down. In a perfectly understood system, these two numbers should match exactly. The energy exiting the nebula as light and particle flow should precisely equal the energy entering it from the pulsar's slowdown. For the crab, this correlation is famously clean, one of the most elegant in all of astrophysics, a testament to the power of conservation of energy. But is it perfect? As our instruments grow more sensitive, hints of a subtle mismatch are emerging. The total output we measure may not perfectly align with the total input we calculate. The discrepancy is tiny, buried within the margins of error, but it persists. It whispers that something in our accounting is still amiss. This imbalance forces us to consider three unsettling possibilities. First, we may simply be missing a significant energy reservoir. Are we underestimating the power carried away by the nebula's vast, invisible TV halo, or by neutrinos we cannot detect? Could there be a substantial amount of energy going into bulk kinetic motion, pushing the entire nebula forward, that we have not fully accounted for? Second, our measurements might contain hidden errors. Calibrating the absolute brightness of an object 6,500 light-years away across dozens of different telescopes and energy bands is a monumental task. A slight miscalibration in the extreme ultraviolet or the far infrared could throw off the entire sum. Third, and most profound, our understanding of the energy conversion processes themselves might be incomplete. We assume the pulsar's rotational energy is converted with near-perfect efficiency into magnetic fields and particle acceleration. But what if a fraction of that energy is diverted into something else, like heating a hidden core of cold matter or sustaining exotic quantum processes in the neutron-star's interior? This energy budget is the ultimate test of our comprehension. A perfect balance would be a triumph, confirming that we have catalogued every major phenomenon and understood their connections. A confirmed imbalance, however small, would be an even greater gift. It would be a bright arrow pointing toward a hidden chamber in the crab's labyrinth, a sign that a fundamental piece of its story, and perhaps of all pulsar-wind nebulae, remains waiting to be discovered. That elusive imbalance in the cosmic ledger is the final proof of the Crab Nebula's greatest, most beautiful irony. This celestial object is simultaneously the best understood and most profoundly mysterious entity of its kind in the entire sky. For over 1,000 years of human observation, it has served as our premier cosmic laboratory, a nearby, brilliant testbed for the physics of extreme environments. We point every new telescope, from radio dishes to gamma-ray observatories, at its glowing heart first, using it to calibrate our instruments and validate our theories. It is the textbook example, the gold standard, the celestial yardstick against which all other supernova remnants and pulsar-wind nebulae are measured. And yet, with every new generation of technology, with every sharper image and more sensitive detector, this familiar neighbor does not become simpler. It becomes more complex. Each answered question spawns 3 new, deeper mysteries. The gamma-ray flares, the flickering knots, the missing reverse shock, the ghostly infrared dust. Every solution we propose is met with a contradictory observation. This is the living laboratory paradox. The very traits that make the crab so perfect for study are the same ones that ensure it will never be fully solved. Its proximity means we see staggering detail, revealing a chaos we would miss in a more distant object. Its brightness means we can monitor it constantly, catching its every tantrum and whisper, each one a deviation from our neat models. Its youth means it is still violently active, a storm in progress, not a frozen fossil. Its complexity is not a bug in the system, it is the fundamental feature. The Crab Nebula is not a simple experiment with a single variable. It is the universe conducting 100 different high-energy physics experiments at once, all within the same 10-light-year-wide chamber. The pulsar's wind interacts with the supernova debris, which is itself interacting with the interstellar medium, while magnetic fields twist and snap, and particles are accelerated and re-accelerated in a turbulent cascade. Isolating one process from this maelstrom is like trying to listen to a single instrument in a symphony played during a hurricane. This relentless confounding is not a failure of science. It is the engine of discovery. Every time the crab defies a prediction, it forces us to refine our understanding of fundamental physics. Those impossible gamma-ray flares pushed theorists to rethink the limits of magnetic reconnection. The pulsar's erratic spin-down challenges our models of neutron-star interiors, realms of density and pressure we can never recreate on Earth. The nebula's chemical patchwork is rewriting our understanding of how stars die and scatter their elements. The crab does not give us clean, easy answers. It gives us better questions. It acts as a ruthless editor for our theories, discarding the simplistic and forcing us to embrace nuance, dynamism, and interconnectedness. In its beautiful, tangled filaments, we see the universe refusing to be reduced to a single equation. It is a reminder that true understanding is not about putting a puzzle together until the picture is complete. It is about realizing the puzzle is alive and the picture is forever changing. Our greatest laboratory is not one we control. It is one that watches us back with the brilliant, unforgiving eye of a star that died a millennium ago, still teaching us what it means to be curious. So this is the portrait that emerges from 50 different angles. The Crab Nebula is not a quiet museum piece, a static monument to a long-past explosion. It is a living, breathing, and violently dynamic engine, a cosmic paradox that grows more enigmatic the closer we look. We have traced the furious spin of its pulsar, a city-sized star that stutters with unpredictable glitches, hinting at a hidden superfluid sea within. We have witnessed its monstrous tantrums, gamma-ray flares that double its brightness from regions where our physics says they should be impossible. We have mapped its invisible skeleton, a magnetic field of stunning order twisted into chaos by 1,000 years of turbulent motion. And through it all, we grapple with the fundamental ledger, the subtle mismatch between the energy going in and the light coming out, a whisper that something in our accounting is still profoundly wrong. Every mystery we have explored is a thread in a single, tangled tapestry. The flickering knots, the silent radio zones, the ghostly infrared dust, the missing reverse shock, they are not isolated curiosities. They are interconnected symptoms of a system where the past explosion is still wrestling with the present engine, where order and chaos are locked in a permanent, beautiful struggle. This is the ultimate lesson of the crab. Our greatest cosmic laboratories are not clean, controlled environments. They are messy, active, and defiantly complex. And the probe into its heart is far from over. The next generation of eyes is already turning toward Taurus. The James Webb Space Telescope, with its infrared vision, is peering into those cold, dark knots, searching for the molecular seeds of creation within the wreckage. The upcoming Cherenkov telescope array will capture the highest energy gamma rays with unprecedented detail, watching the particle accelerators in action. Each new instrument is a key for a lock we have not yet found. The Crab Nebula has been our guide for a millennium, and it will continue to be our teacher, challenging every assumption and rewarding every curious glance with a deeper, more wonderful puzzle. Which of its 50 strange phenomena left you most astonished? Was it the pulsar's impossible speed, the nebula's deceptive calm, or the haunting idea of dust surviving a stellar apocalypse? Share your thoughts below and subscribe to join us as we continue exploring the deepest mysteries the universe has to offer. The cosmos is full of engines like the crab, each with a story to tell and each one waiting for us to listen.